Hi everyone, my name is Cláudio Dias and I'm a principal tunnel engineer currently based in Madrid. I'd like to start by thanking my friend Tiago Souza and Geotechnicall Brazil group for inviting me to deliver another presentation for their channel, and this time with the additional challenge of being in English. For today's presentation, I'd like to talk about sprayed concrete tunnels, an introduction to its design and construction. I hope you enjoy this video. The origin of the sprayed concrete as a material started over 110 years ago, when the American inventor Carl Eaton Ackley created a double-chamber cement gun to spray what at the time became known as gunite. Its first application was to rehabilitate the facade of a museum in Chicago, where Carl was working creating anatomic models of animals. The method had initially several issues, and it took until 1911 to be patented. Gunite was brought to Europe by Karl Weber, a German who had lived a few years in the United States, where he learned about gunite, and in the 20s patented in Germany a method for spraying dry mix concrete. Around that time, the method had already been used in the United States for stabilizing rock tunnels. In the 30s, there is the first use of gunite in the UK and several other European countries. In the 50s, the dry mix concrete arrives in Brazil for research in structural rehabilitation by IPT in São Paulo. The next 2 decades are followed by several developments in materials and equipment, particularly the swing tube concrete pump that enabled the creation of the wet mix shotcrete. In the 60s is developed in Austria the new Austrian tunneling method for rock tunnels. The 70s sees the first use of NATM in Brazil for the Ferrovia do Aço and Rodovia dos Imigrantes tunnels. In the 70s also it sees the research worldwide focus on accelerators and admixtures to improve performance and durability of the sprayed concrete. In 1994 it happens in London the collapse at Heathrow Express Tunnel using an ATM method, which resulted in very heavy fines to designers and contractors. And even though the collapse was not due to the NATM, it led to the ban of this terminology in the UK, which was replaced by SCL. SCL stands for sprayed concrete linings, and in the case of the UK is used both for materials and also for the tunneling method that we will speak a little bit later. In 2008 in Norway there is development of spraying robots that you can see in the image. In 2012 it starts in London, Crossrail construction that use permanent sprayed concrete linings for stations. In 2020 the ITA Working Group 12 published the permanent sprayed concrete linings guidelines. Sprayed concrete has different requirements and constituents than cast in situ or precast concrete. This is mostly due to the compressive strength performance requirements. This table shows typical class of shotcretes used in Europe, where the class C2835 and the class C3240 are typical shotcrete class used in tunnel projects. For shotcrete, the first hour is critical to ensure safety and stability in tunnels, whereas the first 24 hours are critical to ensure durability. As you can see in this image, the regulations recommend upper and lower limits to ensure that both stability and durability are ensured. And the different colors here represent different concrete mix from the Crossrail project. As every project has different requirements, thus every sprayed concrete mix must be optimized through trial prior to construction can start. In terms of the sprayed concrete mix, this image shows a representative distribution of its different constituents. Considering Crossrail shotcrete mix, you can see that the fine aggregate is normally between 40 to 45% of the total weight. Coarse aggregate is between 25 to 30% and normally limited to 10 millimeters maximum particle size. Cement is between 15 to 20%, water between 5 to 10%, steel fibers less than 2%, and then the admixture and accelerators also less than 2%. These may have the alkali-free accelerators, hyperplasticizers, nanosilica, hydration control elements, internal curing elements, and lately now is incorporating crystallizing agents to make the shotcrete more impermeable. In a very simple way to equipments. In this image we can see a typical equipment used to spray dry mix in a small job. The second image shows a wet mix spray pump unit. This third image can see the manual application of the wet mix in a tunnel, for example to spray the regulating layer. And in the last image we can see a robotic application of the wet mix also in a tunnel. Nowadays we try to avoid using dry mix in tunnels, since this method generates more dust than the wet mix shotcrete. Now I would like to show you the state-of-the-art in terms of equipments for spraying concrete, which includes a total station and shows in real time the shotcrete thickness to the nozzle man, as you will see in the following video.
Normet brings a new groundbreaking technology to the market. Smartscan will help to control sprayed concrete layer thickness and reduce concrete usage significantly.
Tämän tyyppinen hanke, kun puhutaan pitkistä tunneleista, niin ruiskubetonin rakenteisiin käytettävä betonimäärä on yli 20 000 kuutiota.
Me ei päästä maahan tippuvasta hukkaroiskeesta käytännössä enää nykymateriaaleilla hirveästi alemmas. Ne on kehittynyt niin paljon, niin ainut järkevä kustannussäästökeinohan on nimenomaan mennä sinne vahvuuksille.
Smartscan is integrated in the SprayMac, providing layer thickness info to the operator instantly after spraying, which removes the need for time-consuming probing at a later stage.
Betonin menekki pystytään minimoimaan ja saadaan ruiskutettua oikeat kerrosvahvuudet.
Smartscan offers automated tools for logging, optimizing, and reporting for the sprayed concrete process.
Se näkee nuo vahvuudet paljon helpommin tuon skannerin kanssa. Löytää ne omat liikkeet sille koneelle, että tietää, että minkälaisella syöttöillä, millä liikkeellä saa minkälaisen paksuuden betonia tuonne seinään ja kattoon.
Ja se, että me saadaan ihan reaaliaikainen skannaustulos työmaalle ilman, että siitä on mitään työtä keskeyttävää häiriötä, se on yksinään jo semmoinen osatekijä, mille löytyy vaikka mitä käyttötarkoituksia.
In any type of tunnel, we excavate a hole in the ground and create what is called a settlement trough at the surface that you can see here in this image. Looking in detail at transverse direction, we can see that the region excavated tries to move inwards, what creates a settlement at the surface with the shape of the inverse Gaussian curve. In terms of longitudinal direction, we can see that at a certain distance from the tunnel face, the settlement starts to build up and destabilized after the tunnel phase has passed. Typically, these distances are plus minus 2 diameters. In order to design tunnels using NATM or SCL methodology, it's very important to understand the Convergence confinement method developed in the 80s. This method imagines the ground behaving along these curves, the ground reaction curve, initially behaving in an elastic way, then the deformations increase rapidly to plastic deformations. So at the moment we arrive with the tunnel face to this region of the ground, it's very important to install a stiff support as soon as possible. That's why it's so important to use a material such as shotcrete to make sure we have a stiff early age strength, and the sooner we install it, the better, to make sure you maintain the properties of the surrounding ground and to use the surrounding ground as part of the support system. Greater skill is needed to avoid rock loading than to oppose it. Indeed, heavy support systems often generate the excessive rock pressures they are designed to resist. This sentence by the Austrian tunnel engineer Ziha summarized the philosophy behind NATM and SCL methodologies. It's very important also in these methodologies optimize spans and geometry, making sure that the geometry is circular as possible, a quick ring closure, as we saw in the previous slide. This image here shows different face splits to make sure we are reducing displacements and stability issues with the excavation. The support selection, it's very important as well. Rock soft ground classification to make sure we have different supports for different class of the ground that the tunnel has to go through. Ground improvement and dewatering whenever necessary to support the excavation. Monitoring all the displacements and make sure we can have a quick action. A dynamic design and using experienced professionals. With all these principles combined, we can build caverns such as this one, the Stepney Green Cavern, 2013 in London, with 180 square meters. So in summary, both NATM and SCL methodologies count for flexibility and adaptability. In terms of the excavation and support sequence in a tunnel, we can see in this image, first we have the excavator removing the ground. In this case, we have the top heading bench and invert. This is done in several advances that we call round lengths, typically of 1 meter. And then we have the spraying works. The shotcrete thickness is built up by several layers. Here we have an example. In this case, we have the primary lining, which, as we saw in the beginning, has higher early age strength requirements. Then we have a fiberless concrete mix to protect waterproofing. And then in the case of using shotcrete for secondary linings, we can have also fireproof requirements. To make sure we reduce the water ingress, and since the joints are normally the weak points in any SCL tunnel, we can start at joints as in this example. In any tunnel project, it should be everyone's top priority to reduce health and safety risks. Since spraying works have the risk of fallout material that can hit workforce, it's important to use exclusion and restriction zones as detailed in this Crossrail best practice document that is available online. SCL activities also produce a lot of dust and noise that should be mitigated and require the use of specific personal protective equipment. Good ventilation must be provided, especially during the spraying works and after it. There is the risk of working with pressurized lines, risk of working in confined space and near heavy moving plant. As every project is different, it's very important to assess the risks ahead and plan and mitigate the risks as much as possible. Ultimately, the experience, train and risk assessment and method statements are paramount to keep the workforce safe and healthy in a tunnel project. In terms of the SCL tunnels design approach, we have the double shell lining, where in the short term both the ground load and water loads are applied to the primary lining, and in the long term both ground load and water loads are applied to the secondary lining. This is because the primary lining is considered sacrificial in the long term. We have the composite shell lining, where in the short term is the same, but in the long term the ground load is divided between the primary lining and secondary lining, and the water load is applied to the secondary lining. We have the composite shell lining with Foley effect, where both the ground load and the water load are applied at the extrados of the primary lining, which allows to reduce the thickness of the secondary lining. And we have the single shell lining approach. This is typical of a hard rock tunnel and where a secondary lining is not required. Moving now to design considerations of SCL tunnels. The level of detail of design depends obviously on the phase of the project, client requirements, and local construction preference. Key aspects that need to be defined by designers start with definition of the geometry, normally driven by space proofing requirements, and the phase split, driven normally by the size of the tunnel and stability. In this example, we have two tunnels. It's also very important in this case to assess the minimum distance between these two tunnels to ensure stability. Definition of round lengths and of enclosure, as we saw in a few slides before. SCL thickness and toolbox items. For toolbox items, we can use ground improvement and dewatering techniques. Thickness are normally driven by structural checks. This is an example of checking bending moments. Reinforcement, there are several solutions going from wire mesh to microfibers and steel fibers that are more popular nowadays. On the use of steel fibers, there is the recommendation by the CVT in Brazil published last year. Durability for these is good to ensure a high density shotcrete mix. Fire protection whenever necessary can be achieved by using synthetic microfibers. Transient waterproofing, monitoring. Impacts to existing utilities and infrastructure normally require the use of advanced 3D soil structure interaction models that we will see in the next slide. The control of groundwater contamination zones whenever these exist. In terms of complex piece of design, we can deploy three-dimensional soil structure interaction models and structural models. These are normally used in case of multi-stage construction sequence to model complex geometries such as junctions, collars, and enlargements. In this example here, we can see a shaft in the tunnel being excavated nearby and where we deployed Plexus 3D to assess it, to optimize SCL, to assess surface settlements, to assess impacts to existing utilities or infrastructure. Some of the most popular packages for three-dimensional soil structure interaction include Plexus 3D, MyGTS, Flat 3D, RS3, and Abacus. For structural models, these are normally used for secondary linings, and the most popular package includes SAP 2000, Strand 7, Strap, Midas, and Robot. Here is an example of a SAP 2000 model for secondary linings. There is a trend for fully three-dimensional soil structure interaction to be industry standard for complex design elements in a few years. Moving now to talk about permanent linings using shotcrete. You may note the example of this famous station in Stockholm, opened in 1957. This is a rock tunnel using shotcrete and then painted in an artistic way. So we know that permanent sprayed concrete linings are a reality for over 50 years in rock tunnels. Moreover, the development of materials and equipments led to an increase in quality and durability of SCL, and now most of the projects require 120 years lifespan. The permanent sprayed concrete linings in soft grounds are also becoming a reality. There are a few examples in the last 10 years. The Crossrail project that we already spoke about, the Strathfield in Australia, Serra do Cafezal in Brazil. The ITA Working Group 12 published in 2020 the guidelines for permanent sprayed concrete linings. This document here that you can access online. This document refers that about 50% of the permanent sprayed concrete linings are in Europe. About 56% of the permanent sprayed concrete linings are used for roads or mining. Also, very importantly, this document refers that permanent sprayed concrete linings could have a 20 to 50% lower carbon footprint than double shell linings and help our industry to reduce impact to climate change. The sprayed concrete secondary linings, as we see here in this image, can be a good alternative to normal cast in situ concrete secondary linings in some cases. Things to consider in the selection process when deciding between a sprayed or a cast in situ secondary lining are design and construction programs. As you can see in these graphs, they have different activities, each one of these methodologies, construction costs, flexibility and logistics, junctions and complex geometries. Typically, in the case of cast in situ in junctions, these lead to very complex formworks, waterproofing system, architectural requirements, local experience, equipment available, and sustainability. In terms of production rates, the case of the sprayed concrete secondary linings can be up to 3 times faster than cast in situ concrete when compared with a similar tunnel in junction and enlargement. As a summary to this presentation, I would like to comment that both the new Austrian tunneling method and the sprayed concrete linings tunneling method in the case of the UK, they both use materials and equipments in continuous and rapid research and development, as we saw in the beginning of this presentation. The equipments used are inexpensive and easy to mobilize and adapt. Normally just involve the use of road headers, excavators, and spraying robots. There is the design for different scenarios and dynamic response to change. a continuous monitoring for quick adaptation to ground response that makes these methods quite flexible, and the adaptability to different geologies and client requirements. The methods are safe and proven construction methods for tunneling, with ultimately hundreds of successfully completed projects worldwide. Thank you for watching this presentation on sprayed concrete tunnels. I would like to thank once again to Tiago and the Geotechnicall Brazil group for inviting me to deliver this short presentation. Make sure to check out their YouTube channel for lots of interesting videos on other subjects. If you have any suggestion or question, please leave them in the comments and I will answer them later. Thank you and bye-bye.